Hello everyone, welcome back to Z Physics. Today we're going to be solving parts of the British Physics Olympiad round 1 section 2 from 2020. Just a little note that these are not official solutions, they're just my solutions, and if you'd like to have a look at the official mark scheme and the British Physics Olympiad website, and you should do that, please have a look in the link in the description. Okay, well, let's have a look at this question here, which is actually question 5. I chose to start with this one because I just find the topic of circular motion and gravity so incredibly interesting. Okay, well, let's get started with the question. We have a bridge which has a circular cross section. It crosses a river with a certain width, and the height of the center of the bridge above the surrounding ground is 4 meters. What is the maximum speed at which a car can drive over the bridge while still remaining in contact with it? And we're given a hint. And every time we're given a hint, it is a very, very good idea to use that hint. So A, B, and C, D meet at a point S, then AS times SB is equal to CS times SD. Okay, well, first off, let's draw a little diagram. And voila, here is our diagram. Now, first off, have a look. So we know that it crosses a river at a width of 18 meters. So this means the distance A to B will actually be equal to 18 meters. So this means that each of the individual distances, let's say AS is going to be 9 meters, and this guy here is B will also be 9 meters. Now the height above the surrounding ground is 4 meters. So this distance here, CS, will be 4 meters. Now what is my plan of action? My plan of action is to use this geometry rule to figure out what the radius is, because we don't actually know what the radius is at the moment. Once we figure out our radius, we could use the physics of circular motion and mv squared over r to actually figure out the answer to this question. So let's figure out the radius. We know that as dot SB, well, given that we have 2 chords, so this is 1 chord, that's CD, that just coincides with the diameter, and we have AB over here, which is another chord. Well, okay, well, AS is 9, so AS dot SB will be 9 times 9, which is just 9 squared, so 9 times 9, and that will be equal to CS, which is 4 times SD. Now let's call the diameter R, or let's call the radius R, which means that the distance across here, so from C to D, will actually be 2R. So this means that the distance SD from here to here will just be 2R minus 4. So this is going to equal to 9 squared, which is going to be 4 times 2R. Take away 4 times 4, which is 16. So let's do a little bit of rearranging, and what we are going to get is that 9 squared is equal to 8R take away 16, which means that 8R will be equal to 9 squared plus 16, which means that R will be equal to 9 squared plus 16 over 8, which is equal to 12.125 meters. So this means that our radius of the bridge is now found. Now this question is actually asking us what is the maximum speed at which a car can drive over the bridge while still remaining in contact with it? Well, the condition is that the centripetal acceleration has to be equal to the gravitational acceleration. So A centripetal will have to equal to g, and our formula for centripetal acceleration is just v squared over r, and this will be equal to g, which means that v will be equal to the square root of r times g, which is equal to the square root of 12.125 times 9.81, and let's put that in a calculator to get approximately 10.9 meters per second, which is the maximum speed at which we can drive off the bridge while still remaining in contact with it. Okay, well, let's have a look at part B. So we have the Sun orbits the center of the Milky Way galaxy. We're given loads of values over here. Assuming the mass distribution of matter in the galaxy is concentrated mainly in the central uniform sphere, and the Earth lies in one of the arms. So this is us just here. Obtain an expression for the period of the orbit T of the Sun in terms of its radius r, g, and mg, the mass of the galaxy. Well, this is actually just Kepler's third law. Because over here it says to obtain an expression, I'm just going to derive it because I want to make sure that I want to get absolutely all the marks. And we derive Kepler's third law by essentially setting the gravitational force equal to the net resultant centripetal force. Let's call that F centripetal, so mv squared over r, which is our centripetal force, will be equal to gmm over r squared. Now we're also going to use the fact that v is equal to 2 pi r over t, because the Sun will be kind of moving in a circle of radius r. Okay, well, let's do a little bit of math. We're going to cancel out this r. Let's cancel out this mass here as well. And what we're going to get is that v squared is going to equal gm over r. Now let's substitute the fact that v is 2 pi r over t, so therefore v squared will be equal to 4 pi squared r squared divided by t squared, which is equal to gm over r. Now let's do a little bit more rearranging. 4 pi squared r cubed will then be equal to gmt squared, which means that t squared will be equal to 4 pi squared over gm r cubed. Now just a little note, this whole expression, all the m's here were, m was the mass of the galaxy, so let me just write this over here, that in this case this m here is actually the mass of the galaxy, so this is m subscript g, and I'll just quickly change this over here just so that we are consistent with the question. Also, one final thing, because we're looking for an expression of the orbital period t, even though this is Kepler's third law, I'm just going to square root this and leave this in terms of an expression for t. So this is equal to 4 pi squared over g, the mass of the galaxy, r cubed, and this is all square rooted. Now let's have a look at the next part, which is to determine a value for the mass of the galaxy. So to determine the mass of the galaxy, we're just going to use this expression just here, and what I'm going to do is just rearrange that for the mass of the galaxy mg. So mg will be equal to 4 pi squared r cubed divided by g times t squared, like that. Now, because all of these values in all of these astronomical questions are absolutely humongous, then we'll probably need quite a bit of space for the plugging in of the numbers for this calculation. Okay, so let's do this. 4 pi squared, so at least that's easy. 4 pi squared multiplied by the radius cubed. So the radius is 30,000 light years, so that will be 30,000. The value of a light year is normally given in your formula booklet, and remember, you're allowed to use a standard exam board formula booklet, so this will be 30,000 times the value of a light year, which is 9.46 times 10 to the power of 15 meters, and we're going to need to cube this like so, and let's divide that by the gravitational constant, which is 6.67 times 10 to the power of minus 11. And finally, let's multiply that by the orbital period, the square of the orbital period. So I'm going to put a bracket here just to remind me that I'm going to need to square this, which is 200 million years. So that's 200. A million is 10 to the 6. And what I need to do is find out the number of seconds in a year. So 200 times 10 to the 6 times 365 days in each of them. Each of them has 24 hours, and each hour has 3,600 seconds. I'm not going to forget to square this like so. And if we put that into a calculator, we're going to get about 3.41 times 10 to the power of 41 kilograms. So this is an estimate for the mass of the galaxy. How cool is that? Okay, part 3, if the sun represents an average star, estimate the number of stars in the Milky Way. Well, the mass of the sun is about, the solar mass is about 2.0 times 10 to the 30. So we're just going to need to, I'm going to say here is the mass of the sun. Is the mass of the sun. Hopefully this is a number that you are very much familiar with. And let's just divide the two numbers to estimate the number of stars. So what I'm going to do is I'm going to do 3.41 times 10 to the power of 41. Let's divide that by 2.0 times 10 to the power of 30. And we're going to get about 1.7 times 10 to the power of 11 stars. So this is a huge number. It's about 10 billion or so just in this galaxy. Of course, this is just an estimate, assuming that the sun represents the mass of an average star. So I really enjoyed this part of the problem. Let's have a look at the next. Okay, part C, which is all about satellites. So we have a satellite orbits the spherical Earth of radius RE in a circular orbit of radius R. Write down an expression for the speed v of the satellite in terms of rg and the mass of the Earth. Explain the physics needed to obtain your expression. Okay, well, let's explain the physics as well. So in order to obtain the speed of the satellite, what we're going to be setting, we're going to be looking at the net force. So the gravitational force, will be equal to the net centripetal force. Our gravitational force is given by GMM over r squared. Maybe we'll just add a little bit of explanation on top because it's asking us to explain the physics. So we can just say that the satellite is under circular motion. So this is actually our net force. So GMM of r squared will be equal to the net force, which is going to be mass times the acceleration. The acceleration is centripetal, which is v squared over r. So let's just rearrange for v, so we can do a bit of cancelling out, and what we're left with is that v squared is equal to gm over r, i.e. v will be the square root of gm over r. One final rearrangement I'll do is, because this is the mass of the Earth, I'll just add this subscript over here just to ensure that we get maximum marks. Okay, part 2, we need to evaluate the speed in the lowest possible theoretical orbit as if it were just grazing the Earth. Now there are a few possible ways to tackle this part, which is part 2. The idea here is that at the lowest possible theoretical orbit, the satellite, so this here is the Earth, it's basically tracking it on its surface, and of course this is impossible because it's going to hit a mountainside or an object, etc. as soon as the rocket or the satellite is launched, so not possible. But the idea here is that if it were possible, then it will be falling at a rate g, and the acceleration g will just be equal to v squared over r, which is the centripetal acceleration if it's moving in a circle. Keep in mind that we could have found the speed v using this equation, so v is equal to the square root of g, mass of the Earth, of r, but we're not given the mass of the Earth, and it's not given in your formula booklet as well, and therefore I'm doing it via this method. So g will be equal to v squared over r. If we didn't use this method, we'll need a way to evaluate g at a given height and then substitute back in here. Anyway, so let's calculate v. So v will be the square root of gr, which is equal to the square root of 9.81, and now for the radius we're going to use the radius of the Earth, which is given in your formula booklet, which is 6.37 times 10 to the 6 meters. And let's plug this into a calculator to get about 7,900 meters per second. So part 3, calculate the period of that satellite's orbit. Well, part 3 is not so bad. All we need to do really for part 3, I'm going to use that v is going to equal to 2 pi r divided by the time period. So remember, the speed is just the distance traveled in one time period, and the distance is just one circumference. So just rearranging for t, this will be equal to 2 pi r divided by v, and that will be 2 pi times 6.37 times 10 to the 6, that's just the radius of the Earth, divided by the speed that we just found out, which is 7.9 kilometers per second, or 7.9 times 10 to the 3. And this will give us about 5,060 seconds. Okay, now let's make up some space for the solution of the next part, which is part 4. So our satellite now instead orbits at a height h, which is significantly less than the radius of the Earth. So that means that if this here is the Earth, the satellite is, I don't know, somewhere here. So the height h is a lot smaller than the radius of the Earth just here. Okay, obtain an expression for the fractional change delta t over t for the orbital period t in terms of h and re. Hence, what is the period of the orbit of the satellite at a height of 200 kilometers? Now, this question I can already tell is going to be using an expansion. Now, how do I know that? Well, let's just write down Kepler's third law once again. We know that t squared is equal to 4 pi squared over gm multiplied by the radius cubed. Now, if we were to add a small amount h, then this equation will then turn into t squared is equal to 4 pi squared over gm, and that will be r plus h cubed. Now, just a little throwback to the beginning of the paper where we looked at important constants and also some very useful mathematical relationships. And the mathematics that we're going to use, or the mathematical expressions we're going to use, is this one. 1 plus x raised to the power of n is approximately equal to 1 plus nx when x is significantly less than that number 1. So let's apply this expansion to our problem. So the first thing I'm going to do is I'm just going to square root the expression. So t will be equal to the square root of 4 pi squared over gm, and this will be r plus h raised to the power of 3 over 2. Now, so let's say that this is equal to 4 pi squared over gm. Now let's take a factor of r cubed because I want to make this expression similar to the expansion that we looked at earlier. I've just written it here, the expansion we looked at the front of the booklet that we can use. So if I take a factor of r cubed, what I'm going to be left with is 1 plus h divided by r. This whole expression is raised to the power of 3 over 2. Okay, well, now what I'm gonna do is just apply this expansion over here on the left. So this whole expression will be then equal to 4 pi squared over gm, and this will be equal to r cubed. Now, rather than 1 plus h over r raised to the power of 3 over 2, I'm going to write down 1 plus my x is h over r, and my power n is equal to 3 over 2. So it's going to be 3h over 2r. Well, hang on a minute. This here was our original time period t. Now, if our time period t is 4 pi squared over gm at an orbit with a radius r, let's call the other one t primed, the radius of r plus h. So this here is actually the orbital period of, let's call that t prime, like so. So we can say that t primed is going to equal the time period multiplied by 1 plus 3h over 2r. So in this question we're actually looking for the obtained expression for the fractional change of time period over the time period. So that's the expression that we're actually looking for. Okay, well, let's find that. We're looking for an expression of delta t over t. Well, if we think about it, delta t really is going to be t prime minus t divided by t, and t prime is just t times 1 plus 3h over 2r, take away t over t. Now let's divide this expression by t. We can essentially cancel out all of those t. So what we're going to get is, that gets cancelled, that gets cancelled, that gets cancelled. But what we're going to get is 1 plus 3/2 hr, and then we're going to get a factor of minus 1 from this t that is cancelled out. If you're worried about this algebra step, you can imagine that you've taken a factor of t out, and what you're left with is 1 plus 3h over 2r, and then take away 1 over here over t, and you've essentially just cancelled that. Okay, well, 1 and minus 1 are going to cancel out as well, and what we're left with is 3h over 2r for the fractional change in the time period. I really like it when we do quite a lot of pretty intense maths, and what we're left with is a nice simple expression, 3h over 2r. Okay, so for part 5, we need to sketch a graph of the period of the orbit t for h, assuming once again that h is significantly smaller than the radius of the Earth. Well, this is going to be some interesting y equals mx plus c analysis. Let's see how those things are actually related. So t prime, the time period at height h, this is what we're actually going to be plotting. This is what's going to be on the y-axis, is equal to t, which is kind of a constant, plus 3h plus 2r. Well, let's just focus on this equation here. So let's solve part 5 just here. And I'm going to say that t primed is equal to t plus t times 3h over 2r. So I'm just going to rewrite this as t primed is equal to t 3 over 2r times h plus t. Well, this is now beginning to look like y is equal to mx plus c. So this will be that, this will be that. H will be on the x-axis, and our gradient will be 3 times t over 2r, and the graph will be a straight line through the origin with the intercept being t. So this is a graph of t prime against h. So some sort of an intercept here, which is going to be the time period. And when t is the time period, this is the time period on the surface. So that's the lowest possible orbit essentially across here. When that's happening, the orbital distance is r. Therefore, this point here will just be the radius of the Earth, r or re. So I've been calling it r throughout here. So I'm just going to say that this here is r, and r is just the radius of the Earth. Okay guys, well, this video is getting really long. Well done if you're still watching, if you're still going through and solving this problem. Now, I'm just going to temporarily stop here this video, because otherwise this video will probably be an hour long until we get to the end. But we've done a lot of really valuable practice for the Olympiad. A couple of key pointers to take: we've been using some expansions. So t prime is equal to, or 1 plus x, sorry, raised to the power of n is about equal to 1 plus x to the n. We've learned how to recognize them. So any sort of little clues that they give us with h being significantly less than r, chances are that probably means an expansion. Hopefully you found this video useful and you've seen some really good and interesting physics in action. Thank you very much for watching. Best of luck if you're sitting the Olympiad this week, and I'll see you in the next video.